When you search for cafes near you on Google Maps, it finds the closest matches in milliseconds, but there are hundreds of millions of places in Google's database. So, how does it work so fast? A naive approach would be to filter through every business by its longitude and latitude, but that's hundreds of millions of comparisons for every search. It would take minutes. So you might think, why not add an index to speed this up? But it turns out traditional indexes aren't very efficient when you're filtering by both longitude and latitude at the same time. To see why, let's look at how they actually work. We'll start with a simpler example, indexing people by age. Then we'll see what happens with location. Most databases use a data structure called a B-tree to implement their indexes. Let's look at a quick example to understand how they work. Imagine we have a simple table called person. It stores each person's first name and age. Now, let's create an index on the age column. This lets us quickly find rows that fall within a specific age range. For example, everyone between 20 and 80. Let's look at what a B-tree built on the age index would look like. Each leaf node contains either the row itself or a pointer to the row on disk. For simplicity, let's assume each leaf node directly stores the rows. These leaf nodes are sorted from left to right based on the column we indexed, in this case, age. Each leaf node also includes a pointer to the next leaf node. Each non-leaf node represents the value range covered by its child nodes. In practice, it only stores the upper bounds of those ranges. The lower bound is implied by the upper bound of the previous sibling. For example, this node tells us that its subtree only contains people whose ages fall between 17 and 48, with 17 being exclusive. So, how does this setup make range queries fast? Let's understand it with an example. Suppose we want to find everyone whose age is between 20 and 80. With a B-tree, this happens in two main steps. Step 1, find where the range starts. It's the first node that's greater than or equal to the lower bound. Using the ranges stored in each non-leaf node as guidance, the B-tree quickly narrows down the search space and lands on the first leaf node within that range. Step 2. From there, follow the next pointers to the neighboring leaf nodes, collecting rows until the values exceed the upper bound of 80. By efficiently skipping irrelevant rows, B-tree helps us find the range without scanning the entire table. Now, let's look at what happens with a composite index. A composite index is simply an index sorted by multiple columns. For example, if you have an index on longitude and latitude, it first sorts everything by longitude, and when two rows share the same longitude, it then sorts by latitude. Here is what the same data looks like in the B-tree. The leaf nodes are sorted first by longitude, and if the longitude are the same, they are further sorted by latitude. That means latitude is only sorted locally, within each longitude group, but across the whole dataset, latitude is not globally ordered. So when you run a query that filters by both longitude and latitude, the index can quickly find rows within the longitude range, but it still has to look through all those rows one by one to see which ones also fall within the latitude range. If the B-tree explanation is still confusing, let's take a look at what happens visually on a map. Let's say you have 8 locations stored in a database. Here's the table with their longitude and latitude, and here's what they look like on a map. When you create a composite index on longitude and latitude, the database first sorts everything by longitude globally. Then, within each group of rows that share the same longitude, it sorts by latitude locally. This is the key thing to understand. Longitude has global ordering. Every value is sorted relative to every other value. But latitude only has local ordering. It's sorted within each longitude group, but there's no guaranteed order across different groups. This means on the map, the index knows how to order all points by longitude. Smaller values come before larger ones. But now look at these 2 points with different longitudes. The index knows which one comes first by longitude, but it has no idea how their latitudes compare, because latitude isn't globally sorted. Now, let's see what happens when we run a location search. We want to find all points inside this box, longitude between 30 and 40, latitude between 10 and 20. For longitude, this is fast. Because longitude is globally sorted, the index can jump straight to 30 and scan until it hits 40. Everything outside that range is skipped entirely. But now we need to filter by latitude. And here's the problem. Latitude isn't globally sorted. The index can't jump straight to 10 across the whole dataset, because there's no single place where all the 10s live. Each longitude group has its own separate ordering. So even though latitude is sorted within each longitude group, we still have to check the latitude in every single longitude group individually. And in the real world, longitude values are high-precision floats, so there could be millions of groups. And that's why we need a specialized index for this kind of workload. A geospatial index speeds this up by treating longitude and latitude together, rather than sorting them one after the other. It splits the map itself into smaller and smaller areas and puts each location into the area it belongs to, thereby treating longitude and latitude as one coherent unit, not two separate fields. When you run a What's Near Me query, it only looks at the areas that overlap your search circle and ignores the rest. If this still feels abstract, don't worry. We'll make it concrete by walking through how a quadtree works. And once you understand quadtrees, the other geospatial indexes will click. They all follow the same basic idea. A quadtree starts with a simple idea. Take the entire map and draw a big square around it. That square contains every business. Now, if that square has too many points inside it, we split it into 4 smaller squares. Top left, top right, bottom left, bottom right. Each point falls into exactly one of these 4 boxes based on where it is on the map. If any of those boxes still has too many points, we split that box into 4 again. And we keep doing this only where needed. The result looks like a patchwork of big and small squares, large squares in empty areas, tiny squares in dense areas like downtown. Under the hood, this patchwork of squares is stored as a tree. The big square at the top is the root node. When it splits into 4 squares, those become its children. Each of those can split again into 4 more children, and so on. So every node in the tree is just a box on the map, with optionally 4 child boxes that cover smaller regions inside it. The leaf nodes, the ones that don't split anymore, are the smallest boxes, and they store the actual businesses inside them. With the data organized into this hierarchy, let's look at how it makes a range query fast. When you run a query that filters by a longitude and latitude range, you're essentially drawing a small rectangle on the map and asking the database, which businesses fall inside this box? A quadtree speeds this up by quickly narrowing the search to only the squares that overlap with your query box. It starts at the root square and looks at its 4 children. For each child, it checks, does this child's square overlap the query box at all? If not, that entire branch is skipped. If yes, the quadtree follows that branch down. At each level, the same process repeats. Most squares don't overlap your query box, so they're thrown out immediately, often 3 out of 4 at every step. By the time it reaches the leaf squares, the quadtree has already pruned away almost the whole map. All that's left are the few tiny squares that actually intersect your query, and the database only needs to check the points inside them. That's how apps like Google Maps find nearby places so quickly, even with hundreds of millions of locations worldwide. And it's the same idea behind Uber finding drivers, DoorDash finding couriers, or Tinder showing people nearby. So let's recap. A naive approach, checking every business, is way too slow. A composite index helps, but only halfway. It can prune by one dimension, but not both at once. Quadtrees solve this by treating location as a single 2-dimensional unit. Instead of searching through points, you eliminate entire regions. That's what makes it fast. If this helped, a like would mean a lot. And if there's a system you want broken down next, let me know in the comments. Thanks for watching.